our last talk before the break is Soichi Omori, seismic thermometry for estimating subduction zone temperatures, a case study in northeastern Japan.
Thank you, Chairman. I'm Soichi Omori, coming from the Open University of Japan, and originally a metamorphic petrologist. And today I'll talk way to estimate temperature of the subducting slab using seismic data. And this work was collaborated with Saiko Kita in Tohoku University. She is kindly providing seismic data for us. Okay, my talk is, first I explained what is seismic thermometry and why I interested in the temperature and the method and the result. So the seismic thermometry is based on the dehydration-induced earthquake hypothesis. This hypothesis means the dehydration reaction triggers the earthquake in the subducted slab. So this hypothesis has almost over 20 years history, and they did the experimental works, and some petrologists also joined to this hypothesis group. And this means, anyway, the dehydration reaction in the subducted slab triggers the earthquake, so the hypocenter distribution corresponds to the dehydrations. And most of dehydration reactions are temperature dependent, therefore, watching the earthquakes in subducted slab is seeing dehydration and also the temperature in the slab. So I use this principle for the thermometry in the subducted slab. So this is an example for use this hypothesis to explain the double seismic zone. This is one of the distinct structure of hypocenter distribution like this. This is a cross-section of Northeast Japan, and the gray dot shows the hypocenter. The double seismic zone shows the upper zone and the lower zone, and the two zones merges toward the depths. And there's a less number, but there's earthquakes between the two zones. So this distribution of the hypocenter can be explained by the reaction, the dehydration reaction in the peridotite plus water system. And this is a phase diagram for this system and the temperature and the pressure, and the blue lines shows the dehydration reactions. So we can apply these reactions to the hypocenter distribution, and therefore the temperature for the reaction is constrained by this diagram. At the depths, the temperature is constrained, so that then we can estimate the temperature in the subducted slab by using the combination of the hypocenter distribution and the phase diagram. So anyway, why I'm interested in the temperature is basically I'm interested in the behavior of water and carbon dioxide in the subduction zone, and also subduction zone dynamics. So this is a cartoon cross-section of the subduction zone, and oceanic plate was formed mid-oceanic ridge and subducting. And the important point is this blue curve means hydration or carbonation of the oceanic crust. At the mid-oceanic ridge hydrothermal activity. Then such a hydrated and carbonated crust is subducted. So Then at the subduction zone, the metamorphism occur, and water and carbon dioxide partly released as fluid. And such a fluid controls arc volcanism and the mechanical and physical-chemical properties of mantle wedge. And other point is if such hydrous or carbonate minerals survive this metamorphism, the water and carbon dioxide enter into the deeper mantle. That's another interest for me, and that's why such process controls the surface environment through the Earth's history. Anyway, the point is how the water and carbon dioxide released or not released. And the key is the subduction zone temperature. Okay, so I will explain the method to estimate the slab surface. This is an oceanic mold crust layer, the temperature. And there is three methods to estimate the subduction zone temperature. And one is metamorphic petrology and numerical modeling. And the third method is dehydration in this aspect method, and I will introduce this one today. And each method has plus and minus signal feature for estimating the temperature. And metamorphic petrology is evidential and covering the Earth's history. We can estimate the former temperature of the former subduction zone, but limited occurrence of the exhumed metamorphic bodies with negative signature for this aim. And the numerical modeling is universal, and it can cover the whole Earth's history if the proper model can be established. But anyway, the model needs to be verified with other methods. So that in this regard, I try to estimate the subduction zone temperature using this method. And this method is the evidential, but if the hypothesis is true, and covering ongoing metamorphism means the present subduction zone temperature. But we cannot observe the previous earthquakes, so that this is not applicable to the past subduction zone. Okay, so next, that's my strategy for estimating the slab surface temperature. The method combines the depth distribution of earthquakes in the mold slab and phase diagram showing the water content in rock. So combining these two data, and I employed a brute force search for the best fit thermal structure to link seismicity and dehydration reactions. Only I use the depth of the hypocenters and the depth for the dehydration reactions. And then the brute force search was done for find the best fit result of these depth distribution of the hypocenter and the dehydration reactions. Seismic data was taken from Kita, works by the Kita and the Nakajima-san, both also from the Tohoku University. And the hypocenters are relocated by double reference method, and it has very high accuracy. Error is smaller than 1.75 kilometer in depth and horizontal here. And this is a cross-section northeast Japan, and this is subducting slab, and the gray dots and the area shows a hypocenter distribution. And I took the earthquake within 2 kilometers from the slab surface and get the depth distribution of the earthquakes. What is a brute force search? And step one, that I generated about 210,000 PT paths to randomly. I mean, it's not randomly, but no physical constraint to generate these PT paths. Only the geometric method was used to generate the such PT paths. And the phase diagram was calculated using the code perplex by Connolly, and using the system to explain enough to explain the mode plus water system. And then finding using such generated PT paths, we can obtain the possible depth distribution of the along a PT path, and we compare the distribution and this depth distribution of earthquakes, and give a matching score to the how both the depth and seismicity and dehydration matches. So I'll show the result, and this is the data for I used is for Northeast Japan, and another one is the Kanto area, just south, but a similar Pacific plate is subducting to west. And this is a cross section for the Northeast Japan, and this is a cross section for the Kanto area. Important signature of the Kanto area is that here is another plate is also subducting. This is a Pacific plate, it's subducting toward north, and therefore there is a lead of the Philippine Sea plate on the Pacific plate. This is very different from the Northeast Japan. Okay, this is the result for Northeast Japan, and this curve is showing the best fit PT path for linking the dehydration and earthquakes. Also, 70% match for the dehydration and the earthquake for the depth. And this curve shows the clockwise turn around the 75 kilometer depth, like this. And then this white area is a totally dehydrated area, so we can't estimate after total dehydration because no dehydration will occur in this area. So our estimate is here, and this is suspected PT path. Okay, this is next is the Kanto area, shows the similar curve, but this area is colder than Northeast Japan, and this clockwise turn is occur deeper than the Northeast Japan at the 90 kilometer depth. While the Northeast Japan, this was 75 kilometer depth. So this is the same result, but projected the temperature onto the cross-section of each subduction zone. And here is a 400 degree and 500, 600 degree. And this is also 400, 500, 600 for Kanto and the Northeast Japan. So such clockwise turn causes quick temperature increase along the subducting slab here. So the 100 to increase in the 100 degree to 5 to about 800 kilometers, but very quickly the increase another 100 degree around this depth. So the counter area is also the very quick heating 100 kilometer depth. So what's the meaning and how can we interpret this such temperature profile? Sorry. So before that, I must compare with previous numerical models to our result. The red curve is by this study. A is the Northeast Japan and B is for counter area. And the orange curve is by previous numerical model, and H03 means by the Hacker for 2003, and S10 means Syracuse to 2010. And Hacker's model is very famous, but just old model and tends to very low temperature for the Northeast Japan. But a newer model is now the yields a high temperature model, high temperature result, but still just lower temperature than this study. But the heating along this depth is similar to our result. There are also the still significant difference between the model and our method is shallower part of the subduction zone that still have temperature, lower temperature. Numerical results show a lower temperature, and our results show higher temperature. And this is an interpretation. Such a signature of the curve corresponds to the subduction zone A, B, C, and this ABC corresponds to the ABC part of the PT diagram. And this corresponds to the colder region and where the subducting plate, subducting slab and the mantle wedge material is decoupled or partly coupled part. And the C part is a hotter region, and this is interpreted by Syracuse and other researchers. This means that the subducting slab and the mantle wedge material is coupled part. So this here, the drag flow of the mantle wedge material is start. So such a mantle mantle wedge flow might be like this shape, and hot material comes to this depth, and the slab contact the hotter material. So the heating by such a corner flow occurs at B depth. So such a depth of B and the degree of heating by the corner flow is a significant feature of the subduction zone. And the previous numerical model is also, this is a key for the numerical model to how to estimate this depth and the degree of the heating. So our method can estimate from the these properties from the observation. Okay, so there's a conclusion, and we propose a new seismic geothermometer for ongoing subduction zone metaphysics. And thermal structure in the Pacific Plate in Northeast Japan and the Kanto area was successfully estimated recently. And the depth and the degree of the heating by corner flow are constrained by this method also. So the Tetsu Kogiso-san will present the integrated model using this result in the next talk. So the implications for this method will be presented in the next talk. Thank you very much.
Sure.
Yeah, I have a question about your assumption. Many people argue intermediate earthquakes are related to dehydration. It's really hard to believe it. Many problems, but there's a relatively new paper by China and Earth. They did the interesting experiments, and they look at how the formation and dehydration of sublimity might be related to either if this causes the unstable deformation, and their conclusion is not. And also there are a couple of reasons to cast doubt about this common belief. And do you have any comments? Because experimental basis sounds like very weak. And if you build your model on this, there are alternative models. Equally, instability in any model, like the thermal runaway, leads to certain temperature similar to dehydration, but physics is totally different. So I'd like to hear your comment.
Yes, but actually for the experiment is limited for the serpentinite, and I just extended the hypothesis to the model. So that's the point, and I want to that point will be clear, and but sorry, I don't know such negative experimental result.
Well, that's very
okay, I will follow that. And, but I have never seen the negative result for this hypothesis. I don't know why, but
that's a negative result.
Oh, okay. I will follow that one.
Yeah.
One more quick question.
Just want to add this. I think for this kind of studies in the future, we should maybe look at more distribution of the dehydrotic stress in the slab more than the places where dehydration of the slab occurs. And this because these intermediate earthquakes are double events. So this means that they need high differential stress. So basically the location of these earthquakes, the epicenters, indicates more where the stress is high. Then, of course, you can have also dehydration.
Yeah, but I think the stress is high everywhere in the subduction slab.
Not everywhere.
But more or less, I mean. And everywhere earthquakes could occur, but the dehydration only define the location of such a failure occur. It's a dehydration, but the dehydration doesn't affect to the stress and also the no mechanical effect, right?
I don't think it's guaranteed that the epicenter tells you where dehydration occurs, but I think it's really 100% guaranteed where the differential stress. The differential stress is high. I think this is a small difference.
Anyway, the seismic zone means such a high differential stress and earthquakes could occur in the zone. Right.
Very quick. We're running very, very late.
Okay, sorry. Well, about the question raised by Sean Colorado, there are some experiments by Tamak and curve showing that there are that much dehydration improvement. But previous work, there are many also experimental data showing that there are dehydration improvement occurring, starting from the experiment by Rheology and Patterson since 1965. After that, there are many experiments, also including my experimental data, showing that indeed there are some dehydration improvement going on. But I think I don't really understand what the Chonam and the Curtis experiment to study. We don't know exactly yet the reason why they didn't see that there is improvement of their specimen. But maybe one possibility, maybe they used totally suboptimized the sample. But I don't know exactly yet. Maybe we need further investigation on this issue. Okay, yes.
Because we're running very late, let's try and have a 10-minute coffee break and come back at 11:15. There are 2 more talks in this session, and then we move to seismology. So let's take 10 minutes.